Hello, this is Nefi Varela, and this is my answer to the fourth question for this fourth unit about the kidneys and the lungs. And I'm really excited because we are reaching to the end, and I'm gonna explain something about, I'm gonna talk about something really, really cool. I'm gonna start describing two physics, chemistry laws. The first one is Henry's laws. And these laws explain how gas will dissolve in liquid. There are gonna be two main things that are gonna contribute of gas dissolving in liquid. The first one is partial pressure, and the other one is solubility. Okay, so we're gonna have a formula for this: partial pressure times the coefficient of solubility. And this is going to tell us how much a gas will dissolve in water. As we increase partial pressure, we will increase this solubility in a liquid, okay? And the second one is Dalton's law. Um, this law explains that in a mixture of gases, all the pressures that a gas, all like individual partial pressures of a gas are gonna contribute to the total of like the total pressure. I don't know if that makes sense. So let's say if I have a gas 1 plus gas 2 plus gas 3 is gonna equal gas total. So that's what this formula is saying. So as we learned previously, pressures, we're going to have several pressures that are going to play an important role in breathing. The pressure in the atmosphere and the pressure in the inside of our lungs. In the atmosphere, we're going to have a pressure of 760 millimeters of mercury. And from that total pressure, a 78.6% is going to be nitrogen, a 20.21% is going to be oxygen, a 0.04 is going to be carbon dioxide, and 0.46 is going to be water. In the alveoli, in the other hand, you'll see that it's a little bit different. Nitrogen is going to be 75. Oxygen is going to be 14. Carbon dioxide is going to be 5.2, and water is going to be 6.2. And we have this phenomena where pressures will want to go from a higher pressure to a lower pressure, okay? And this is going to be really important because, as you can see, we have a higher pressure of oxygen in the atmosphere that we have in our lungs, in the alveoli. So it's saying that the affinity of oxygen is going from the atmosphere, from the environment, to the inside of our lungs. In the other hand, the pressure of carbon dioxide is greater in our lung than it's in the atmosphere. So the affinity of carbon dioxide is going to be to go from our alveoli to the outside. Okay, so that's pretty cool. So everything's going to start here in our mouth. We're going to do inhalation. Eventually, oxygen is going to reach our lungs. Okay. When we have this inspiration, we're going to have about 160 millimeters of mercury. And this pressure will drop eventually to about 120 as it mixes with water. Water is going to decrease that partial pressure of oxygen because we have liquid in our lungs, right? Well, a little bit. Too much liquid is bad. And what's going to happen is that the pressure of oxygen in our lungs is going to be, well, in the vasculature is going to be way lower. It's going to be 40 millimeters of mercury. So now oxygen will want to go from high pressure to low pressure, from 120-ish, 160 to 120 to 40. So we're going to see oxygen getting into the vasculature. And we already said that 2% is going to dissolve in plasma. The other 98% is going to be carried by hemoglobin to be transported to the rest of our cells, tissues that it can help in their function. In the other hand, in the other on the other hand, we're gonna have a pressure of 0.3 of carbon dioxide in our alveoli. But in the vasculature, it's gonna be 45. Why? Because this blood is being carried from our cells that after doing metabolism are gonna increase that like concentration of carbon dioxide, increasing the pressure of carbon dioxide. So now, because we have a higher concentration of carbon dioxide in our vasculature, this concentration will want to go to the alveoli that is gonna be finally secreted in expiration. Okay, so that's what's gonna happen. Eventually, we're gonna decrease this pressure 104. I think that's the pressure that we're gonna have finally in the alveoli. It's gonna go to the vasculature. It's gonna go to the vasculature. We still have 40 here. And then we're gonna have this oxygen carbon dioxide exchange. Okay, where oxygen pressure is gonna drop eventually when it goes throughout all the vasculature to 95. But the pressure of oxygen within our cells is going to be way lower. It's going to be 20. So it's going to get out of the vasculature. It's going to drop to 45. Eventually, it's going to get to the cell, and we're going to have this gas exchange. Okay. So now going from high to low. But for carbon dioxide, I already said that we had a partial pressure of 40 millimeters of mercury. Is going to go to the vasculature. We're going to maintain that pressure. And eventually, we're going to reach these cells. The pressure in our cells is going to be 46. Okay, 46 is going to drop to 40 to 45 as we're going to the interstitial space, and it's going to go to the vasculature because it has lower pressure. So we're going from high to low again. And that's what's going to happen. Eventually, oxygen is going to drop to 45. Carbon dioxide is going to be maintaining 45 also at the point that we reach these capillaries where gas exchange is going to occur in between our alveoli and the vasculature. We're going to have these pressures, and we're going to see that exchange. Oxygen gets in, carbon dioxide gets out. So that's pretty cool how it works. We have an alveolar equation, and this one is used to calculate the partial pressure of oxygen in the alveoli. And there are so many factors that are going to play in this formula. One is partial pressure of oxygen in the alveoli. The other one is going to be the fractional concentration of inspired oxygen. The other one is going to be atmospheric pressure. Then it's going to be about 760 millimeters of mercury. That's mercury. I don't know why I did what I put in here. Millimeters of mercury at sea level. I forgot to mention the fractional concentration of inspired oxygen is going to be 21. I think I already mentioned it previously in the video. Water vapor pressure that is going to be 47 millimeters of mercury. Arterial pressure arterial pressure of carbon dioxide that is going to be 90 millimeters of mercury, and respiratory exchange ratio that is going to be about 0.85. This ratio is going to be obtained by the volume of carbon dioxide over the volume of oxygen. This is a ratio, and this one is dependent of carbohydrate consumption. Usually in Western diets, we don't consume, well, I say we because I'm here, we don't consume a lot of carbohydrates. So that's why this number is closer to 0.8 than to 1. Either way, the ratio will be equal to 1, okay? And also, it is worth to mention that if we increase keto diet, it also will affect this because we will decrease concentration of carbon dioxide. So this respiratory exchange ratio also will drop. So that's the formula. PaO2, referring to the pressure in the alveoli, is going to be equal to the fractional concentration of inspired oxygen times atmospheric pressure minus pressure of water minus the pressure in the arteries of carbon dioxide over the respiratory exchange ratio. Okay, so I plug the numbers in here. So 0.21 times 7060 minus 47 minus 40 over 0.85, and we're gonna have about 120. That is the number that I gave you here. Pretty cool, right? 120. So that how this gonna work when it comes to pressure. Now I'm gonna refer more to air. And instead of talking about pressure, I will describe volume in units of liters. Okay. So liters, milliliters. As we know, we take air from the atmosphere to the inside of our lungs. Okay. So this is gonna be for alveolar ventilation. This cycle is like a recycling cycle, recycling cycle. Um, we're gonna take some air to our lungs, and this air we're gonna call it fresh air. But there is some air that is not gonna reach the alveoli level, and it's gonna stay in our bronchi somehow. And this one is not gonna participate in gas exchange. And this one we're gonna call it anatomical dead space. So I have some numbers here: 150, 350, and this number is going to be 150 for a standard respiration. Okay, when we have I forgot the name, uh, pulmonary ventilation, tidal volume of about 500 and a breathing rate of 12 breaths per minute. Okay, so now we have exhalation, and that's what's gonna happen. We're gonna take out that dead space, and we're gonna take out these 350 milliliters of air, and we're gonna keep 150 milliliters here in our bronchi. Okay, that is gonna become eventually that like new dead space. Okay, so now when we have inhalation, we're gonna take new fresh air. At the end of exhalation and at the beginning of inspiration, now we're gonna take 150 new fresh air, 350 milliliters of fresh air, and now this 150 milliliters of all air is gonna go to the alveoli. This one, 350 millimeters of fresh air, is gonna go to the alveoli, and we're gonna have another 150 milliliters of fresh air that eventually are gonna become that new dead space. Okay, so that's pretty cool. Dead space is gonna be the air that doesn't participate in gas exchange. We have alveolar dead space, and we also have anatomical dead space. Okay, that's referring to oxygen that is not participating in gas exchange. And in total, the addition of those two values is going to give us physiological dead space. So now, to calculate total pulmonary ventilation, we are going to use this unit named tidal volume. Tidal volume is going to be the volume of air that we take in and out in passive breathing. So it's going to be tidal volume times breathing rate. So for in this scenario, it's going to be 150. Well, 500. Sorry, 500 is actually the amount of air that is participating in this gas exchange times 12. That is going to be our standard rate for respiration. 12 breaths per minute. So now alveolar ventilation, another important formula is going to be tidal volume minus dead space times breathing rate. Okay, so alveolar ventilation, if we do the math, we have 500 that is participating in this gas exchange minus 150 that is going to be our dead space. As you can see, it remains constant, time 12, that is going to be in total 350. So that's how we're going to be our alveolar ventilation, that oxygen that is participating in gas exchange in our alveoli. I don't know if what I said is right, but that's the right number. Okay, so as we increase the alveolar ventilation, we are going to increase also the pressure of oxygen. And as a result, we will decrease the pressure of carbon dioxide. This is going to happen as we have rapid respiration. We are going to increase the amount of concentration of carbon dioxide. But when we have deep breaths, like low, slow, I'm gonna say meaningful breaths, we're gonna increase our concentration of oxygen. So it's gonna be as a result, we're gonna have a greater alveolar ventilation. So that's how they're gonna correlate. Rapid ventilation, just think about it, is getting too fast. We're not letting enough oxygen to participate in that gas exchange to reach the alveoli, because we take it out so fast, we take it in so fast that we don't have that like these cycles, as I show you. In the other hand, when we have deep breathing, we are filling our lungs with more air, so we're going to have a greater concentration and pressure of oxygen, decreasing the concentration of carbon dioxide. That was like a tongue twister, guys. I hope you like this. Now, I'm going to describe another ratio that is going to be alveolar ventilation and perfusion ratio, V over Q. V is going to be the air that reaches the alveolar per minute, and Q is going to be the blood that reaches the alveoli per minute. Again, we're talking about the elements that are participating in gas exchange. And as we descend in the lungs from the upper to the lower lung, we're going to see that the concentration, well, the values for V and Q are going to get higher. Why? Because we have higher proximity to the heart, okay? And in the middle, this value, this ratio is going to be usually 1. But the standard ratio for VQ is actually 0.8. Why? Don't ask me. So now, as you can see, these values are going to be about equivalent. In a liter of air, we're going to have about 200 milliliters of oxygen. And in a liter of blood, we're going to have 200 milliliters of oxygen too. Okay? So again, we have these ratios where tidal volume times this is going to help us to get a total pulmonary ventilation. And there's something really important to say. There are going to be some values that are going to affect the amount of air that reaches our alveoli and the amount of blood that reaches to the alveolar tube, affecting these, like their participation in gas exchange. One of them, for example, is pneumonia. By increasing liquid in our lungs, we are increasing volume, right? So we are taking more space, less space for oxygen to participate in this exchange. So we increase liquid, we increase volume, we decrease the air. Okay, for asthma, we have constriction in the bronchi. By having constriction in the bronchi, we are letting less air to reach the alveoli. Bronchitis is going to be inflammation in the bronchi. Again, imagine that we are closing these two. So we are going to decrease also the amount of air that reaches the alveolar. Now, to reduce the amount of blood that reaches the alveolar per minute, there are going to be several pathologies. I'm just going to describe them. They're really predictable to understand, to know what's going to happen. The first one is right-sided heart failure. The other one is cardiogenic shock. Another one is damage in a blood vessel. The other one is a long-term chronic bronchitis at the point that it reaches the capillary, creating some damage in the capillary. And the last one is going to be emphysema, where we have a lot of elastance, but we maintain the amount of blood. So that has something to do more with elastance. We are not letting our lungs to return to their original state. They're getting full. So we have this like stiffness in the lung, if I want to say it like this. So how's this gonna work? Imagine that we have here the alveoli, and here I have a capillary, and by blocking the capillary, we're gonna have less blood participating and in this gas exchange. And this is what is happening in alveolar ventilation perfusion ratio. Finally, the last part of the video, emphysema and chronic bronchitis. So with emphysema, we're gonna have damage in the walls of the alveoli, making them less elastic and enlarged. And this is pretty cool to me. It was really nice to me to learn this because about a year ago, I had like an accident making a barbecue. When I inhale a lot of gas from charcoal, so my lungs got really, really damaged. As a result, I need to use that inhaler. I'm supposed to use that every day. I don't because I forget. So that's what is happening. So we have less electricity. So it's really hard. It's exhausting to do exhalation. Okay. There are going to be several causes for this. One is smoking. The other one are chemicals. The other one are factors that we inherit from our parents. A name that has given to this problem is the pink potters. I think so. And some characteristics of this is going to be labor breathing. Uh, uh, I don't know what I wrote here. Sorry. Barrel chest, shortness of breath, use of accessory muscles to breathe, and frequent respiratory infections. So that's what's going to happen. We're going to have difficult exhalation and easy inspiration because we are decreasing elastance. Okay, so it's difficult to do exhalation. Imagine like okay, finally, chronic bronchitis. This happens with irritants and cigarette smoke, where uh, where we have okay, sorry. So where we damage our cilia and they become fewer, and eventually they cannot clear mucus. So mucus starts building in air passages, and as a result, we make a thick bronchial wall. Actually, I think that's what happened to me, not the other one. That's leaning more to this one. And eventually, we have a hyperplasia in the globate cells, also named dyspnea, so abnormal breathing. This is going to be characteristic by cough, overweight, and cytocytic, yeah, elevated hemoglobin, epiphyseal edema, breathing noises while breathing, and wheezing. I think that's how you say it. So in other words, just to summarize, with emphysema, we're increasing elastance. So we're decreasing elastance, sorry. So returning to our graphs for the previous video, by decreasing elastance, we don't need a lot of pressure to increase volume. So inhalation is easy, but expiration becomes pretty hard. And in the other one, even when it's not the same as increasing elastance, we are increasing a stiffness in our bronchi. Again, we need more pressure to fill our alveoli with oxygen. So we have heavy breathing and it's easier to have exhalation. So that's pretty much it. This unit was super cool. I hope you liked it. And that's it.